Section 4.5 is the dimension of a vector space, or we'll define what that is, and we'll see a nice theorem about it. I've actually included a little bit of section 4.4, which is coordinate systems, and I didn't think it was relevant as a, or necessary, I would say, as an entire section on its own. We just need a definition and a result or two from that section. The techniques of this are a little bit strange looking, but let's nonetheless introduce coordinates of x relative to a basis. So far we've known coordinates of x vectors in terms of coordinates of the standard basis, right? So if we had a vector v, or I guess I could call it x to be more consistent, it would have components x1, x2 possibly, in Rn, of course, just to keep it, or R2, just to keep it simple. And we know that we can decompose as standard basis vectors as follows. And it turns out that our coordinates in the standard basis vector are these constants x1, x2, or the weights of our linear combination of our standard basis vectors. Well, we've already seen that we don't need to use just the standard basis vectors in order to form a basis for an n-dimensional real space, right? We don't need these two E1 and E2 vectors for R2. We could pick any two linearly independent vectors for R2. So in other words, for something like this, we might want to decompose in terms of the basis 1, 2, and maybe 0, 1. Right? Just changed it a little bit. These are also two linearly independent vectors, and they form a basis for R2 as well. And we could express the vector x in terms of the linear combination of these two vectors, right? Namely, I think we can see that somewhat easily here. This would be x1 times this vector, and I think if we do this correctly, it would be plus, we're going to need x2 on the second one. Well, I'm doing this one from scratch. We don't really need to do that, but you can see what the challenge is, and that's the challenge we're going to deal with down below. So I think my point is made that it's not quite obvious how to do it, especially for a general vector, but we're going to see down below some nice techniques to take care of that. So, right, we can form a basis. It doesn't have to be the standard basis for a real space, an n-dimensional real space, and yet we can still talk about the representation of a vector in terms of that basis. It doesn't have to be the standard basis anymore. And that's what this in section 4.4 was all about. So let's see this proper definition and do some nice examples that will probably be a little easier to follow. So suppose we have a basis B consisting of B1 to Bn for a vector space V, and X is some vector in V. And the coordinates of x relative to the basis b, or the b coordinates of x, is a more succinct way of saying that, are the weights c1 to cn, in other words, the scalars, or the real numbers, typically, such that x is equal to c1 b1 plus all the way up through cn bn. So that made sense for the standard basis vectors, right? The vector x1, x2, well, it has weight x1 against this standard basis vector, that's b1, the basis vector, and then x2 times b2 for this second basis vector, and those are, we only have two basis vectors, so there it is. So our vector in standard coordinates consisted of x1, x2. Right? If we change the basis, it's going to consist of different weights in order to form that same vector x1, x2. So let's see how that happens down below in the example. So we're given, in this example, two basis vectors, b1 and b2. Not too dissimilar from what I was actually kind of writing earlier, but nonetheless. And we've got a vector x equal to 5, 2. And we're told that the two vectors b1 and b2 are the basis for this space, or for their space. Looks like R2 in this case. And then find the coordinate vector xb of x relative to b. right? So the coordinate vector of x relative to the basis b. So the challenge is this, what we're looking for is, so we have to just note that x and beta coordinate, or sorry, b coordinates has C1, C2 as its coordinates, right? Where C1 and C2 are the weights of the linear combination of these two vectors, right? It's just as it looks for the standard basis vectors. And as I started to write for non-standard basis vectors in my sort of non-example at the beginning there. But what our challenge is to figure out what C1 and C2 are so that we know how our given vector is expressed in terms of these two basis vectors. So that's the idea of B coordinates. B coordinates are these weights right here that cause this to happen. Well, if we look at what we're actually doing, this is really just this 2 by 2 matrix, putting these two columns together, times the vector C1, C2 equals 5, 2. That's an AX equals B matrix equation. We write it down in that sense. I've left it as a linear system, right? C1 plus 0 times C2 equals 5. So we're trying to solve for C1 and C2 through this. And in this case, it's just as well to do it as a linear system because of this 0 is very helpful here. So it gives us sort of a top-down back substitution, but or maybe a forward substitution. And we're just able to solve for C1 right away. And then we can solve for C2 following that. So typically, though, I think we see the algorithm that we're going to run. We'll say, well, all right, we'll take our basis vectors for whatever our basis is that we're considering, and then we'll take our vector, and we'll figure out its b coordinates in terms of our basis b by writing the augmented system 1, 0, 2, -1 with those we're reading by rows with the augmented column of 5, 2, put in echelon form and determine what each of our coefficients C1 and C2 are. And when we have our solution, C1 and C2 make up our two entries for the beta coordinates. I believe I've got that written somewhere. Oh, maybe I didn't. I missed that. So let's keep in mind, this is one of our targets. X in B coordinates is C1, C2, once these weights are written down. That's our goal, is to figure out what these weights are, because that, of course, is our B coordinates for X. So our coordinates for X in terms of the basis B. Now, another interesting thing that comes out of this, we can look at this map right here, and we can consider what it actually does, right? Where we solve for C1 and C2, what is this really telling us, right? We get out these real numbers, right? C1 and C2 come out as these real numbers. So what this mapping actually does is it's the coordinate mapping from B coordinates to standard basis coordinates. So that's a nice way to look at that. So in other words, B coordinates to standard basis coordinates. So if I apply this 2 by 2 matrix to either of my basis vectors, I should get my standard coordinates back, or my standard basis back. In this case, the 1, 0, 2, -1 matrix, we apply it to 1, 2, you'll see that you get, by matrix vector multiplication, 1, 0, right? When you do the first row times that vector, or sorry, 1 for the first entry, and then 0 for the second, 2 minus 2 for the second row times that vector. So you get 1, 0, so it's your first standard basis vector. Then when we apply it as matrix vector multiplication to B2, we get 0, and then 2 times 0 and -1 times -1, we get 0, +1. That's our second standard basis vector. And that's one way of looking at what this matrix right here is for our in our change of coordinates problem here. So that is that's a matrix transformation, right? So we can see that this means that if we consider a coordinate mapping or the coordinate transformation from B coordinates to standard basis coordinates, we see that it's going to be a matrix, and this will generalize. And we know that matrix multiplication is linear, so we know that this is a linear transformation. So, and that's a general result, but I think we've seen it by example here, and that's sufficient for the intuition for the proof of that theorem, or at least for acceptance that will be the case in general. So that coordinate transformations are, at least this type of coordinate transformation is a linear transformation. And that's a useful tool in what's to come. So getting to section 4.5, I actually sneak a 4.4 theorem in the middle of this page because that's a necessary item here. It's looked over in the forming of these notes. But let's define first the dimension of a vector V. So if a vector space V is spanned by a finite set, so we have a finite number of vectors in a set that spans V, then V is said to be finite dimensional. The dimension of this finite dimensional vector space, written as dim V or dimension of V, or maybe we use those braces, maybe we don't sometimes, doesn't really matter, is the number of vectors in any basis for V. So any basis, not any spanning set. So remember, bases are the minimal list of vectors that would span V, right? It's the fewest number of vectors we can find to span a given space. So we go by the number of vectors in any basis for V. So if V is the trivial vector space, V equals just the set containing the zero vector, then its dimension is said to be 0. If V is not spanned by a finite set, then we say that V is said to be infinite dimensional. So the set of all polynomials is infinite dimensional, right? We have 1, x, x squared, x cubed, and so on up to infinity, or x to ever larger positive integer powers for a basis for that space. And that's not a finite set. So there's an example of an infinite dimensional vector space, just the set of all polynomials. And then most of our Rn spaces are, we'll see, are actually n-dimensional. They'll have n vectors in their basis. And actually, I think we've already seen that or established that as a previous result. But this theorem here actually comes out of section 4.4. It's one last thing we need about coordinate mappings. It's just a useful rule for, or a useful theorem for proving this 4.5 theorem below it. But if we let B be a set of basis vectors B1 to Bn for a vector space V, then the coordinate mapping from x into beta or B coordinates for x is a 1-to-1 mapping from V onto Rn. We've already established that this coordinate mapping is linear, right? But we can also see that we could also prove somewhat easily that it's a 1-to-1 and onto mapping. The textbook covers that proof in case you're interested. And anybody who's taken a discrete math course or worked with 1-to-1 and onto functions realizes that this is a bijection, right? So we have essentially we'll have an isomorphism between V to Rn, which means, maybe we don't delve into that too much in this course, but that means that for any vector space V, it's essentially the same space as Rn, is the way to think of it. An isomorphism means that not only does each item in V map onto Rn, but also the algebra that takes place in V is the same that takes place in Rn. In other words, if we combine two vectors in V and get a result, then their images in Rn, if we combine those two images of those two vectors in V, we'll get the image of the vectors in V that are vectors in V that combine to give us, or that we'll get the image of the item in V that was combined to get in V. So if we had x plus y in V, its image would be the same as taking the image of x and the image of y and adding that together. So one way of thinking about it is that any vector space V is completely analogous to Rn. Maybe we'll just leave it at that. So what we really want to talk about is the dimension here, though. So if a finite dimensional vector space has a basis consisting of n vectors, then any set of more than n vectors is linearly dependent. Okay, so this is the idea of paring down spanning sets, possibly, right? So, or any set of vectors, really. So that should seem more or less obvious, right? If we have a set of vectors in R3, we've seen several times now that if there are 4 or 5 vectors, maybe we'll say 5 vectors in that set of R vectors from R3, then we're going to have a linear dependence among those vectors. Even if we have 4 vectors that are in R3, we're going to have linear dependence there. Now, whether or not there will be 3 linearly independent vectors, so that depends on the set. But we know that if we have more vectors than the number of entries, we have linear dependence among those vectors. That's an old result from previous sections. So let's prove that for a general finite dimensional vector space. So we let U1 through UP be a set of vectors in V, which has more than n vectors. So P is greater than n. So then the coordinate vectors. So we immediately talk about the coordinate vectors of U1 to UP in terms of B are linearly dependent in Rn. Right, so we remember that changing from a given basis, making our coordinate mapping for the x for the b coordinates of any given vectors u1 through up is a one-to-one mapping onto Rn. So we immediately can do that for some set of basis vectors b for v, and we know that these are going to be linearly dependent in Rn. Remember, this is a map into Rn. Well, these are going to be linearly dependent because P, we have P of these vectors in Rn, and P is greater than n. That was what we started out with. So we know that we have linear dependence in Rn. This is the old fact that I cited before. So that being the case, we have constants C1 through Cp, not all of which are 0, such that the linear combination of these vectors is equal to 0. Right? This is our linear dependence equation right here, for not all 0 C1 through Cp. So since the coordinate transformation is linear, as we've already seen, or at least talked through, we have that we can rather than have each of our translated our b coordinates for u1 through up in this linear combination, that can be expressed as one b coordinate for the linear combination of c1 u1 through cp up. So that's just by linearity. It looks it's using the scalar multiplication property of linearity, and it's using the vector addition property of linearity, all in one big step to write this. Well, remember that this statement here is the set of weights of this whole vector here that writes this vector in coordinates of this 0 vector here in Rn. So what that means is that we've got this expression here is actually equal to, well, if it's equal to the 0 vector, then all of our weights against our basis b vectors are 0. Well, and so we're equal to the 0 vector over here. So since some of our C1 through CP vectors weights are not 0, then U1 through UP are actually linearly dependent, right? So we're able to achieve through our linearity of the coordinate transformation this expression. Really, we can move from here to here to say, well, yeah, we've got that this thing's equal to the 0 vector, but I mean, and we have some non-zero C1 through CP, so this is clearly a linearly dependent relationship. So for any vector space V that has dimension n, if we have more than n vectors in a set from that space, a subset of that space, then we know that we have a linearly dependent set. Now that it should intuitively, it's just fine, and really the proof, you don't really need the proof to accept that, yeah, of course this is the case, because really when we think about things, vector spaces V are essentially analogous to vector spaces Rn, right, as long as the dimension of each space is the same. But nonetheless, it's got a thorough proof and result that is necessary, because vector spaces V are new to us, right? So that's the toughest sort of result to get through in this section. I'll sketch the proof of this subspace dimension theorem that's given here. This is a kind of easy one to see once we get through that previous theorem we looked at. So if we let H be a subspace of a finite dimensional space V, any linearly independent set of vectors in H can be expanded, if necessary, to build a basis for H. And also, H is finite dimensional, and dimension of H is less than or equal to V, or the dimension of V. So if, let's start out with the easiest case. If H is just the trivial subspace, just containing the zero vector, well, then the dimension of H is 0, and that's going to be less than or equal to the dimension of V, depending on what V is. Maybe V is also the trivial subspace or trivial vector space. If not, then of course the strict less than holds. So this is true in that case. Now, if H contains this set of vectors U1 through UP, and these vectors are linearly independent, yet they don't span H, right? Yet their span is not equal to H. There's something in this space, in this subspace H, which U1 through UP cannot generate. Then there exists that something, find that vector, whatever it is, and just add it to the set, right? So it's not in the span, because if we pick this vector, or we can find a vector that's not in the span, and if it's not in this span, then it's linearly independent, and we can make some probably contradiction arguments to show that it would be linearly independent. And we can add it to the set as a p+1 element, and then we can check again if the span of that set with UP all the way up through UP plus 1, if that doesn't span H, well, then we can look around and find another vector that's linearly independent and not in the span, and we can add that, and we'll preserve linear independence of these vectors U1 through P plus K, however many times we have to do it. We have to do it K times. And once we do get a set of linearly independent vectors, and this is equal, then we stop. So of course, that's the way we would extend a subset of the subspace to be a basis for H. So and that's that. And then another quick argument in the book file takes care of this one. H is finite dimensional, and its dimension has to be less than V's dimension. That one probably comes intuitively, right? R2 is a subspace of R3, and R2 has a dimension 2, and R3 is dimension 3. Now, the way we'd have to write those R2 vectors is we'd have to have a 0 in the third component. That's one way of saying it, one way of writing it. So let's see. The basis theorem down below, I don't bother to sketch through some proofs, but I will talk through some of it. We let V be a p-dimensional vector space with p greater than or equal to 1. And the first statement here is that any linearly independent set of exactly p elements is automatically a basis in V. Okay, so what we're saying is that if we have a linearly independent set of p vectors of p elements, right, and V is p-dimensional, then this set then is automatically a basis for P. So if we have P vectors that are, so argument by contradiction would tell us this. Suppose we have this set of P elements that are linearly independent, right, for this, in this P-dimensional vector space V. Well, if the set doesn't generate V, it doesn't span V, well, then we can do the same method we did above and go looking for a vector that's not in the span and add that to the span so that it will span V. Now, the problem with that is we would be adding that vector, it would be linearly independent, right? If we were in the case where we weren't actually spanning V, then we find one that's linearly independent, add it to the span. Now we'd have p+1 elements in a set that's linearly independent. Well, that contradicts the theorem above, right? We wouldn't set, that contradicts the fact that, well, it actually contradicts the definition of V being a p-dimensional vector space, right? We'd have p+1 elements in it that are linearly independent, and that's impossible. Sorry, it contradicts the theorem on the previous page. That's what I meant to say, right? it would have more vectors in it than the dimension, and we'd have a linear dependency. So that's, you know, an informal argument by contradiction there. And the second statement in this theorem is any set of exactly p elements that spans V is automatically a basis for V. So this is sort of the opposite thought. This is saying that if we have p elements in this p-dimensional vector space and they happen to span V, then they're automatically a basis for V. And really the only thing we have to argue here is that they're linearly independent of each other. And the argument here is to say that, well, if they have a linear dependence, then we take an element away and then we have p minus 1 elements in it, and they're linearly independent now. And if they still span V, then that contradicts the fact that V is p-dimensional. That would tell us that V is p minus 1 dimensional. That's a contradiction to what p's dimension is. So I think the book argues probably somewhat similarly to that, but they have it written down and maybe a little bit more formal than how I've explained it here. But nonetheless, this is a useful tool. Now we'll know that if we're dealing with a set of linearly independent vectors, and there are p of them, and we're in a p-dimensional space, well, then we know we have a basis automatically. And these are cementing things that we were kind of just doing by intuition and a little bit of guesswork previously. But now we've got a nice concrete, well, no pun intended, basis for work in this realm now. So the dimensions of the null space of A, the column space of A, and the row space of A, these are so relevant that we actually give them names. So the rank of an m by n matrix is the dimension of the column space. Okay, we're going to find that this is pretty easy to come by. The nullity of A is the dimension of the null space. So for a quick example, we can find the rank of a matrix A by just going to the number of pivot columns, right? So the dimension of the column space is really, when we formed our column space, we picked our pivot columns because that's all we needed. I think we eventually had a result that stated this, but we argued intuitively for a while with that, those cases. And then the nullity of A is the number of free variables. Again, that's another thing we do. If you recall what we do to write down the solution to the homogeneous problem, we pick all the free variable vectors, and those are really, that's what forms our solutions, right? Or we have two free variables and we isolate them as scalars times vectors. If we have two free variables, we'll have two vectors, right? So this translates really nicely to counting up the number of vectors we have in a null space. Now, at some point in the past, we've also proved that these are linearly independent vectors in each of these spaces, the column space and the null space, when we pull them from row echelon forms, right? So if we look at this matrix A given below, looking for the rank of A, it's the column space of A. Well, we look for the number of columns with pivot positions, right? Or we just count up the number of pivot positions just as well. But these three columns here have pivot positions. None of the others do. So these three columns make up our column space, right? We can see that we could argue that they're linearly independent. I think we've already worked through those in detail in the past. Given the nature of echelon form, they are linearly independent. Now, opposite that, any variables that didn't have a pivot column in them, or any columns that didn't have a pivot column in them, represent columns of for free variables. So x2 and x4 in this case end up being free variables. So we have a null space that's going to consist of two linearly independent vectors, and that's going to give us a nullity of 2. So 3 column space vectors and 2 null space vectors gives us rank and nullity as follows. Now, here's the interesting thing. We see that this was a 4x5 matrix, and this is the more important part. We have 5 columns. So we see that there's some conservation here, right? We don't have any in between. It's either a column that's contributing to the column space, or it's a column that contributes to the null space. And another thought about that kind of might help. It might make sense to realize that, yeah, if we don't map to something non-zero, so these two vectors map to 0, or these two, it's not these two vectors, but these two columns represent will help us find vectors that map to 0. But this represents the dimensions that we map into 0 with, and then the other 3 are columns and represents the dimensions that we map into non-zero items with. And so yeah, we're either mapping into a 0 or we're not. So that's why this sort of conservation here is held. Now, this is formalized in the theorem below, right? We have the dimension of the column space and the null space of an m by n matrix A satisfy the equation rank of A plus nullity of A is equal to the number of columns in A. So there it is. We have an m by n matrix. Really, that's just, we can just write equals n right here. It's equal to our number of columns, and n by n matrix is n columns. So for the 4 by 5 matrix A above with 5 columns, right, n equals 5, we saw that the rank of A is equal to 3 plus the nullity of A is 2, and that actually added to 5, right? We've already pointed that out. So that's formalized now in the rank theorem. So now it's quite nice to go looking for null space and column space things, because we know they have this complementing nature, that their sum should be equal to the number of columns, and each of these columns then has a meaning to us, right? This represents the dimension of, these 3 represent the dimension of the space for which we map into in a non-zero way, and then these other 2 vectors represent the dimension of the space that we map into in a or that we map to a 0, right? So one more example in this section is to find the nullity and rank of the given matrix A right here. So of course, we want row echelon form. So we do that. We arrive at this row echelon matrix here. And we do the same technique we did before. We look for our pivot columns. Here's one. This column has a pivot position. That's that -5. And then no other column has a pivot position. So we have rank 2. The number of columns we have in our column space is 2. And then our null space represents free variables. Well, we have no pivot position in these columns, so we have free variables here. And that leaves us with a nullity of 2. So nullity 2, rank 2, and this is really that easy. So now without finding our column space or our null space, we can determine what the dimension or what the dimensions of those spaces are. That's a nice tool to use if that's all we're looking for. So bottom example is just a couple conceptual questions. If we have a 4 by 6 matrix with nullity 2, what's the rank of 4? Or remember that when we talk about nullity and rank, we're talking about this is from the number of columns, right? This is places we map to, right? Do we map to 0? It's the how many things, or what's the dimension of the space that maps to 0? That's the nullity, right? That's 2 in this case. And then that leaves us the dimension of things that don't map to 0 necessarily, right? Which is the rank of A. So in order to find this, we use the rank theorem. 6n equals n, which is 6, is equal to the rank of A plus the nullity of A. We know the nullity of A is 2. So then the rank of A when we solve for it is 4. So that's a lot more talking than is probably necessary. You probably saw it here when you realized that with nullity 2, n is 6. We're going to have rank of 4 to make up 6 from 2. Okay, can a 4 by 6 matrix have nullity 3? Well, absolutely. Yeah, 4 by 6 matrix can have nullity 3. Since 3 is less than or equal to 6, it could have nullity up to 6. Okay, so that's just fine. If the nullity is 3, then the rank is 3. Right? 6 minus 3 is 3. So sure, that's fine. If we had a 6 by 4 maybe, and they ask, can the nullity be 5? A 6 by 4? No, the nullity couldn't be 5 because 5 is greater than 4. We can't have a nullity that's greater than our number of columns. So those are just some thoughts for these situations. So the invertible matrix theorem, we append that just 5 more properties to this now. It's just, nice to just have this whole long running list of equivalences. If you go back to the last section that mentioned this, I don't exactly remember when that was. We'll see probably in determinants. And see that we can add this to it. Now these are pretty straightforward additions because they really just follow from the definitions that we have, these new definitions that have come up in this chapter, right? So A is an n by n invertible matrix. Then we have this new equivalence. The columns of A form a basis of Rn. Well, if you remember previously in the invertible matrix theorem, we know that the columns of A are linearly independent by one of our equivalent statements for the invertible matrix theorem. We also know that the columns of A, or the span of A, is equal to Rn, also from a previous equivalence statement. So those two together imply that the columns of A form a basis of Rn. And in turn, this statement that the columns of A form a basis for Rn imply the opposite. So now we've got this new statement we can use in the invertible matrix theorem, that its columns will form a basis for Rn. Now, the column space of A is Rn. Well, this is equivalent to the columns of A spanning Rn, right? So that's taken care of. Let's see, the column space, the rank of A is equal to n. Well, if the column space of A is n, that's equivalent to the rank of A being equal to n, right? How many vectors are in a basis for the column space of A if it's equal to Rn? Well, Rn has n basis vectors in any basis. So that means that column space of A has n vectors in its in a basis of it. So then its dimension is n. So the rank of A is n. Okay, these are really, they're almost so straightforward that writing down a proof for them is a little bit difficult to do because it's just so fundamental. The nullity of A is equal to 0. Well, the rank theorem implies this, right? This comes from the fact that, or the I guess I call it the rank theorem, but the dimension rank theorem from the previous page would imply this. If the rank of A is equal to n, and we have n columns, then the nullity of A is 0, right? The dimension of the null space is 0 because the rank has filled out the entire dimension, or matches the dimension. So nullity has to be 0. And then if the nullity is 0, well, that's by definition, that means that the null space is the trivial space, which just contains the 0 vector. So that concludes section 4.5, the dimension of a vector space. Remember, a key part of it was to map from a general vector space V to some space Rn. We've seen that any vector space V can be mapped by a coordinate transformation to Rn. That mapping was linear, one-to-one and onto, which makes it a linear bijection. So if anybody is familiar with bijections, we know we have the exact same number of items from one to the other, and in some sense, they have the same count in some sense, or cardinality, if you're familiar with that. If not, we just recall that the coordinate transformation allowed us to show that any vector space V is analogous to some vector space Rn. And we define the dimension of such a vector space, and it's going to match the dimension of that vector space Rn that it maps to n. And then moreover, we dug a little bit deeper to see that a set of basis vectors will have the same number of elements in it for an n-dimensional space every time. It'll always be n basis vectors. And then we extended that into matrices to see the rank and nullity of a matrix and connect that overall to the dimension of it. So now we have a very clear and concise set of rules for figuring out the column space of A, or knowing information about the column space of A and the null space of A. And section 4.6 will continue this consideration of coordinate and change of bases, and that'll end chapter 4 for us.